Hello everyone. So in this lecture, we will discuss different models and we'll see physical and probability models. Okay. So the contents would be, first of all, we'll see the need of these models. Then we'll come to physical models and probability models, right? So first of all, what is the requirement of studying these models? So we can say why we need to study these models in this subject of data compression. So as we have already discussed, a good model, if we are having a good model, then it can be very useful for us in estimating the entropy of the source. Okay, so and definitely later on it will help us to create different encoding schemes that would be really efficient, right? Then if we are having good models for if we know the source of the data, and if we have created a good mathematical model, then definitely it will lead to developing more efficient compression algorithms, right? So through these models we can develop techniques that can easily manipulate the data using different mathematical operations. Okay, so we can define different mathematical operations also, and we can effectively manipulate this data. Then the last, this is one of the requirement for a good model. So a model would be, it should be close to reality, right? It should depict the real situation for a particular kind of problem or particular kind of real life scenario, right? And once we are having such model which is close to reality, so definitely it will lead to developing very efficient compression algorithms and encoding schemes, right? So this is one of the requirement of these models, right? Now we'll start with physical models. Okay. So as the name suggests, this physical models basically this is derived from the word physics, right? So in these models, our concern is about the knowing physics of source of the data generation. So we should know how the data is being generated, how the data is interrelated, right? What is the relationship among the data? Okay, so all these things we'll focus upon. So if we are knowing the physics of data generation, then definitely it will help us to construct a required mathematical model and also a good mathematical model, right? So here one thing that is to be that is to be considered, that physics of data generation is actually not that simple. Okay, so if we are not able to have that physics of data generation, if we are not able to understand that in such an efficient way, then what in that case what we'll do, we'll obtain a model that will actually be based on some kind of empirical observation, right? Related to the statistics of the data, right? So in that case, we have to give certain model, and we have to use some kind of empirical observations, right? Let us take one example of speech production system. So suppose we want to encode the speech. So here, first of all, we should know how the speech is being produced. So we should know the physics of this speech production process, right? Then only we can give a more mathematical model for that. And later we can use that model for the encoding purpose also, right? So first of all, we should understand the whole process of this speech production, and then only we can create a good mathematical model. Okay. Then if we take another example, like we are having some telemetry data, okay, and we want to develop a model for that telemetry data. So what we should know, first of all, we should understand the underlying process, the whole process that how this data is being generated, how this data is interrelated, right? Is there any dependency among the elements of the data, or they are, whether they are independent or they are dependent. So all these things, first of all, we have to understand, right? So if we take one example, like suppose we want to develop a model for uh, electricity usage. Okay. So first of all, we should understand like what is the pattern of electricity usage, right? At what time the electricity usage is high, at what time it is low. So all these things, first of all, we have to consider, we have to understand. Then what we can do, rather than storing the actual readings, what we can do, we can store the difference between the actual reading and maybe the average reading. Okay, so this kind of efficient algorithm for encoding we can develop if we know the physics of the data, right? So now let us start with the probability model. So again, if as the name suggests, these models are actually based on the probability, right? Let us consider a situation where we do not have any information about the source, right? So in this case, we'll have two assumptions, right? Suppose we want to, we want to generate the different letters, right? So we'll have two assumptions. The first assumption will be of independence, okay? That every letter is independent. Let's say we are generating two letters, A and B. So in this case, we are considering that A and B would be independent. So there is no dependent of A on B or vice versa. So that is the first assumption. The other assumption is that the probability of occurrence of these two letters or all the letters would be same. So independence and same probability, these two assumptions we are having. Like if we take one example, let's say I'm throwing a dice. So in that case, if I have the same probability assumption, which means probability of getting 1 or 2 or 3 or 4 or 5 or 6 would be same. That is 1 by 6. Okay. If we take another example, let's say we are throwing a coin. So in that case, the probability of getting head or tail would be same, right? So these two are the examples of equal probability situation, right? Now, if we are having these two assumptions of independence and equal probability, then such kind of model we'll call as ignorance model, right? Now, our probability model is actually a kind of extension of this ignorance model, right? So if we remove the equal probability assumption, that means now the different events may have different probability. So if we remove the equal probability assumption and keep the independence assumption, right? So one assumption we have removed and we are keeping the other assumption intact. So the model that we'll get is actually the probability model, right? So let us consider a situation where we are generating some alphabets, A1, A2, A3, and up to A of M. So in the probability model, we'll have the probabilities where the probability of occurrence of A1 is P of A1, then P of A2 for A2, P of A3, that is the probability of occurrence of A3, and so on, right? So this is the these are the set of probabilities that we are getting, and they will actually form the probability model, right? And as we have discussed during the introduction of information theory, so once we have these probabilities, so we can easily find out the entropy of the source also. And that will be minus sigma P of AI into log P of AI to the base B, right? So if we want to encode our information in bits, then we'll take this B as 2, or we can take B as 10, or maybe exponential base we can also take, right? Now there may be a situation where we have to remove the independence assumption also, right? So suppose we are having some data that is actually not fit with our independence assumption. So in that case, we can also find out better compression scheme also if we discard this assumption, right? So if we are discarding the independence assumption, then we can have better compression schemes. But in such scenario, what we have to do basically, we have to come up with some way to describe how the dependence is there among the different letters, right? So if we are having two letters and they are dependent, so we have to describe that dependence also with some sort of technique. Then only we can develop better compression schemes. So I think if I quickly recall, so in physical models, we are concerned about the physics of the data, how the data is being generated, right? How it is interrelated. And in probability models, we are concerned about the probability. The main thing is about the probability of occurrence of different events, right? So that is all about physical and probability models. Thank you.